we go, is, here I've got it written as if psi is a function of x, y, z, and t, but of course I can put it in spherical coordinates, and we could write the potential as a function of spherical coordinates in general. But we're going to be interested in specifically solving the hydrogen atom wave functions, and that means we're going to place our proton, the nucleus of the hydrogen atom, at the origin. And the potential energy between the proton and the electron is only going to be a function of how far it is away, right? Only a function of the spherical coordinate r. And so with that in mind, we're going to specialize to cases of what we call central potentials, where the potential only depends on the spherical coordinate r. And we're going to try to find separable solutions. And we sort of went through most of this step by step last time. We're going to try to write psi, which is a function of the three spatial variables in t, as a product of a function of r times a function of theta times a function of phi times a function of t. And we did that. We were able to separate this partial differential equation that depends on 4 variables into 4 separate ordinary differential equations. And you may think ordinary differential equations are hard to solve. Generally, that's true. And we're going to have to resort to series solutions in a lot of cases. But they're not nearly as hard to solve as partial differential equations. So this is a major achievement. The t equation stuff works exactly the same way it did in 1 dimension. So when you separate variables into time and spatial stuff, the separation constant is called E, which we later interpret as the energy. And this is the same exact equation we got, ordinary differential equation for t as a function of little t. And then there's a radial equation. Boy, it looks complicated. We'll think about that in a few cases as we go. There's an angular equation. That one also looks complicated. And we're going to have to do a series solution for it. The phi equation is actually pretty simple. Capital phi of little phi. It looks like a harmonic oscillator kind of equation. So this, the same way we did in chapter 2, we can just straightforwardly solve it. It's what's called a separable differential equation, and we can just, oh, I forgot my equal sign there. It's supposed to be t of t equals this function. I'm not going to put in a normalization constant here because we need one overall normalization constant for psi. So let's not normalize the t's. There's supposed to be an equal sign there. I just didn't type it in for some reason. The r equation we're holding off on because r depends on exactly what the potential energy is as a function of r. And by the way, I should mention, does anybody not have the photocopied version of this notes? I gave them out one day a few class periods ago. They're also on the website. So we need to know the potential energy function as a function of r to solve this. So we're going to put that off longest. The theta and the phi equations don't depend on the potential energy, so we can just solve them straight away now. And once we do this, we'll be able to get our separable solutions, which, just like before, are the definite energy solutions. The phi equation's easy to solve. It looks like a harmonic oscillator. There are 2 linearly independent solutions, but they're both of this form, so we're going to initially, m could be any integer in order to satisfy the boundary condition phi at 2 pi is equal to phi at 0. We have to, and we solve the theta differential equation using a series solution. And, the details probably aren't shown in Griffiths. I can't remember. I certainly didn't talk about them. But they're called the what did I say? Associated Legendre functions, the PLM, which are functions of cosine theta, which means they're functions of theta. And they end up being polynomials in cosine of theta, possibly times a sine of theta, which could be written as a square root of 1 minus cosine squared theta. So they're really just functions of cosine theta, almost polynomials, or polynomials in a lot of the cases. And we then applied some boundary conditions, and we found out that in order for the wave function to be continuous at all angular locations, including theta equals 0 and theta equals pi, And, you know, when phi jumps from 0, 2 pi back to 0 as you go around there, m has to be an integer, we found out, and then L can only be positive, or sorry, non-negative integers. L equals 0, 1, 2, non-negative integers. It could be a negative integer, but you don't get a different solution there. So we just kind of throw away the negative integer solutions. All right, so that's a summary of what we found out last time. And I think at the end, we were just talking about the people conventionally rename the product of the theta and the phi functions, right? So they're part of this overall solution here. They're sort of the function of the angle in 3 dimensions, right? What angle you're at, both theta and phi. And people call those functions the spherical harmonics, and they're usually given the name y. And since theta depends on those quantum numbers L and M, and phi depends on M, we use the subscript L and superscript M. So it's just a product of those two. Whew, okay. Now, when we multiply all this stuff together, you know, certainly at t equals 0, we're going to want to normalize. And once again, the normalization condition, if we were in Cartesian coordinates, we would have magnitude of psi squared as a function of x, y, and z times dx, dy, dz. But we got to put in this other stuff in spherical coordinates, right? The spherical coordinate volume element. And by convention, people normalize this function by separately normalizing the radial equation and by normalizing the spherical harmonics. So in other words, if I force it, if I make this integral equal to 1, in other words, if I put a constant out in front of that YLM and find the constant that makes this integral equal to 1, I would call that a normalized spherical harmonic. And those are conventionally the ones people use. And then I'm going to separately normalize the radial solutions. Of course, when you normalize those, you got to put the r squared in there next to the dr, because all of that's part of the spherical volume element. And so let's just practice with one of these normalizations, just so you kind of get the idea here. Here's a particular spherical harmonic. We're just doing problem 1. And we're supposed to find the normalization factor for it. We're looking for y10. People typically voice the subscript first and the superscript second. So when I say y10, I'm first giving the L and then the M. This worksheet, Alvis and Gracie, is on the web site, but I wasn't sure if we were going to get to it on Monday, so it's under Monday's date. We're doing problem number 1 for the Monday worksheet. So we're given PL of cosine theta, which is PL of theta, is P10. L equals 1, M equals 0 is cosine of theta. And Y10 is YLM is PLM times e to the I M phi. So let's normalize it. It's easy, but you got to kind of decode a few things before you realize how easy it is. I've left up here the fact that normalization means forcing this double integral to be 1. Okay, so we essentially have to do that double integral and require that it's 1 with an a out in front and see what a has to be.
Dr. Kelly, the video's blurred.
Oh. Thanks for letting me know. I'll turn it off and turn it on again.
Oh,
Looks like
there we
it's
go.
not aimed right.
Be good. But, oh,
So what I've written on the board is, almost done. What's written on the board is this requirement that this equals 1. So I put an arbitrary constant. Oh, I need it. Sorry, I don't have the right thing up on the board. I'm trying to write down this, but I blew it along the way. So let me write it. I need the magnitude of YLM squared times sine theta d theta d phi. I forgot to square it, right? So let's go back here. We're supposed to be using y10 and normalizing it, right? So we're going to put a constant out in front of it, and then this should be the magnitude squared here. So a is going to be squared. I need this thing squared. It's real, so I don't need an absolute value. I need to square this thing. M is 0, so e to the 0 is 1, right? This is 1. And we're told that this thing is cosine of theta. That came from a table that I showed, very quickly flashed earlier. They're more complicated functions. So when we square it, this is a cosine squared of theta. Okay, so I need to simplify this down, set it equal to 1, and then solve for a. So let's do that. That's a squared. There's no phi stuff in there, right? Because this just goes to 1 here. So the integral d phi gives me a 2 pi, right? I'm integrating phi from 0 to 2 pi. There's no phi stuff in there. So it just gives me 2 pi. And then I have an integral from theta equals 0 to pi cosine squared theta sine theta d theta. How do we do that integral? Yeah, we do a u substitution. For example, let's let u equal cosine theta. Then du, derivative of the cosine, is minus sine theta d theta. And so this thing right here is minus du. So let's replace this. I get an integral. I get minus the integral of u squared du from u equals, when theta equals 0, u is equal to 1, right? When theta equals 0, cosine of 0 is 1, so u is equal to 1. And when theta equals pi, cosine of pi is minus 1. Maybe you don't like those backwards limits, but I've also got a minus sign, so I can use that minus sign to flip the limits, right? I could also say that's plus the integral from minus 1 to plus 1. I'm just keeping less minus signs there. Okay, and then that is u cubed over 3 evaluated between minus 1 and 1. So that's 1/3 minus 1/3, which I think is 2/3, right? Okay, so let's just now continue over here. I have 4 pi, a squared times 4 pi over 3. I'm going to demand that this equals 1. And that means the appropriate a is root 3 over 4 pi. Looks like it agrees with my solution. And therefore, to finish up the problem, we're supposed to write down the normalized version of y10. So the normalized version of y10 should be normalization constant, root 3 over 4 pi, times P10 as a function of theta, we were told that's cosine of theta, times, well, m equals 0 and e to the I m phi is e to the 0, which is 1. So I don't need the exponential part on there. It just simplifies to 1. So there's our normalized version of y10. And you can do this, you know, it becomes more painful when L and M are larger. Any questions on that stuff? I'm just forcing us to do one normalization so that now I can go to, well, not this one. This is our PLM. So we're looking at the case 10. So here's this. You can see, well, things could be much more complicated, but you know, we dealt with this one right here. And here are the combined YLMs, and here's the one we just worked out here. It wasn't too bad. If you had all day, you could fill out this table and figure out what the normalizations are, okay? And somehow, you know, Griffiths, I don't think he really explains this, but he says, you know, the normalization factor can be written out explicitly in terms of L and M. So if you know what L and M are, you fill it into this formula and you get the normalization factor, except that there's a sign, this little epsilon out in front is either a plus or -1. And he's got some rule in the book for when it's +1 and when it's -1, depending on L and M. But you know, the general form is e to the I m phi times one of those functions of cosine theta and possibly a sine of theta. And a square root, and then there could be some pluses or minuses out in front. That's what that epsilon is. So we just showed how to do this once. I guess if you think about it clearly enough, you can once and for all figure out what the normalization constant is for any L and M. I've never worked that out myself. I don't think Griffith shows where it comes from either. Questions on the YLMs, the spherical harmonics? So anytime you separate any partial differential equation in spherical coordinates, the YLMs are going to appear. So they're not just a quantum mechanics thing. They appear in all fields of physics where you're talking about things that are functions of 3 dimensions, partial differential equations. So the classical wave equation or Maxwell's equations, you're going to see these appearing in there too, where fields are functions of r, theta, and phi. Where you have spherical symmetry. Okay, so again, this just tells us part of the overall shape of the wave function. It tells us what's happening as a function of theta and phi. So this is displayed in the conventional way where z is up. As we go down around a particular sphere, that's theta going from 0 to 2 pi. And then phi varies from 0 to 2 pi as you go around the equator in that direction, right? And this is showing, well, because normally there's an e to the I m phi here, and we can't really draw complex numbers very easily. So where the person I stole this from on the web took instead the real part of e to the I m phi. In other words, this is the real part of the spherical harmonics as a function of theta and phi as you vary L and as you vary M. I'm only showing the positive m's here because they're only showing the real part. The negative m's look the same in this picture for these kind of things. So, you could just imagine, let's check one. Let's see. Lost contact with my clicker again. P1, let's take a non-trivial one. P22, that's L equals 2, M equals 2. The theta dependence is sine squared theta, okay? So here's 2, 2, sine squared theta. That means sine squared theta has a 0 up at 0, right? Because when theta equals 0, sine is 0. And it's got a 0 at pi, down over at pi, right? And as it's going around, this e to the I m phi, where m equals 2, is oscillating around, and its real part is going positive and negative and positive and negative and positive negative as you go around. So you can kind of get the idea that as M gets bigger, it oscillates more quickly as you go around in that direction. And as L gets bigger, it oscillates more time as you go from the North Pole to the South Pole. That's the general kind of idea. Okay. So that's telling us what the angular part of a wave function is doing for different L's and M's, if you have a separable solution. Now we want to go on and talk about the radial equation for a particular potential, right? It involves V of R. And so we need to know the potential. And we're going to do, well, okay, before we talk about a particular potential, it ends up that there's some simplification in that ordinary differential equation. If you change the variable from, which is what we're ultimately interested in, to U of R. U of R is just R times capital R. In terms of U of R, as a differential equation for U of R, the radial equation looks like this, which is kind of nice. I can see something that looks like a kinetic energy term, right? This is a minus h bar squared over 2m d squared dr squared of the of the function, plus something times u equals E times U. So that almost looks like kinetic plus potential equals E times the function, except that the potential energy function is messed up, right? We wanted this potential energy function. We got this extra funky thing there. People, because it has that same form, people often talk about this as, they call it the effective potential. When we're looking for the functions of R, this thing is behaving like a potential would if we were just solving a one-dimensional kind of equation, right? And people sometimes call this thing that depends on script L the centrifugal term of the effective potential. Our goal, let's not worry too much about the effective potential, but rather our goal is to solve this simpler differential equation for U of R, and then we'll simply divide it by R to get the R of R that we wanted. Right? So this is always going to be a nice way to go. When we normalize R of R, we need to multiply by R squared dr. That comes from the spherical volume element. But because R squared times R of R squared is just U of R squared, if instead we go ahead and just normalize U of R, we don't put in that R squared factor out in front of it, and normalize it kind of the usual way, integrating from R equals 0 to infinity and letting it equal 1, that will automatically normalize R of R in the right way. So oftentimes people will just go ahead and normalize U before they divide by R, just because it's half a step easier. Okay, so we now need to know what the potential is in order to solve for R of R. And here's the example we're going to do as a stepping stone to get to the hydrogen atom, to sort of show how this stuff fits together, because it is confusing even in this simple case. This is called the infinite spherical well. Remember, our infinite well in one dimension, the potential was 0, and then suddenly went to infinity forevermore. Here it's the same way, except our location in 3 dimensions where the potential is 0 is the inside of a sphere, and everywhere outside of that sphere, the potential is infinity. So we call it an infinite spherical well. And we want to find the energy eigenstates and eigenvalues. In other words, we want to solve the time-independent Schrodinger equation for those product solutions, which is R of R times YLM of theta of phi. Those will be the states of definite energy. So let's just go ahead and do it. It seems like something drastic happens at R greater than A. In that case, just like before, we have to have psi equals 0 out here in the case where the potential is equal, goes to infinity. And then the interesting part is where R is less than A, inside the sphere. Okay, we want to find out what U is as a function of R and then divide out R to get R as a function of R. So in this case, there's a script L in here. L has to be a non-negative integer. And in just a second, just to get some intuition, we're going to specialize to the L equals 0 case first. Then we'll go to the more general solution later on. We're also going to, in this case, a definition has been made to simplify the differential equation like we've done many times before. We're going to define k to be root 2me over h bar. E appears in the radial equation. We traded it out for a k, okay? And when we find our solutions, only certain k's are going to be allowed, just like only certain k's were allowed in the one-dimensional infinite well. Okay, so to get a feel for things, let's first set L equal to 0. If we set L equal to 0, hey, that really simplifies things. So let's try to find the special solutions that have integer L equal to 0. That's just going to give us our good old harmonic oscillator differential equation, ordinary differential equation, but for a function as a function of R. Okay. And we know the solutions are linear combinations of sine of kr and cosine of kr. And therefore, once we got those solutions, we can divide out the r. The idea is if you know u of r, you can divide out the r to get r of r, which is what we're after. And we get sine of kr over r and cosine of kr over r. Why does the one I've x'd out behave badly? And why is the one I haven't x'd out not behave badly? When r equals 0, so it looks like r equals 0 is going to be a problem here. Why is that one not a problem? That is the sinc function, right? That's your favorite L'Hopital's rule kind of thing, right? Where we say sine of kr over kr goes to 1 as r goes to 0, right? So this is perfectly finite because the denominator is going to 0 as r goes to 0, but the numerator is also going to 0 in such a way that the ratio stays perfectly finite. Here, the numerator goes to 1 and the denominator is going to 0. So this thing's going off to infinity as r goes to 0. That would mean, you know, if I'm inside my spherical well, you know, here's the center of the well and the radial direction is like that. It would be like I'm looking for a solution. You know, we don't normally draw things like this, but my solution is going up to infinity as I get close to 0. It's also going to infinity as I approach r equals 0 from that side. And so that function is not going to be continuous. And one of our basic things is that psi's always got to be continuous, at least for the kinds of potentials we agreed to restrict it to. So in this case, this would be a discontinuous solution. So sticking with only the continuous solutions, we can throw away the cosine kind of term. Now, we've found a separate solution for inside and outside. Outside's just 0, but we got to match them up. The potential goes to infinity, so we don't know anything about psi prime having to be continuous, so I don't think it has to be. But psi certainly has to be continuous. And so I've got to make sure that my solution inside matches my solution outside. Okay, when I plug in psi at r equals a, it better go to 0 because it's got to match up with 0 outside, right? So that means the only way for this to be 0, the a is not going to make it 0. Dividing by something can't make the ratio 0. The only way to make this whole thing 0 is to make the numerator be 0 when I plug in r equals a. And so sine of ka has to be 0. And just like before, that means ka has to be equal to an integer multiple of pi. You got to think about this a little bit, right? Why did I say just n equals 1, 2, or 3? Couldn't n be any integer? Why did I throw away n equals 0, for example? There's just a lot of details of little things, and each little argument's not so hard, but you know, you're finding that from last lecture through today, there's like 100 little arguments, and I'm only talking about 10 of them. But you know, this is just an example of like, okay, here's something that got thrown up there. N's got to be a multiple of pi. Well, why can't it be -4, or why can't it be 0? Why did I leave those out of the set of allowed n's there? Yeah, if n equals 0 were allowed, then that would mean k is equal to 0, right, by this equation, if k is 0, sine of 0 is 0, so this whole thing is 0. And that's not normalizable. So we're throwing away n equals 0 to keep it normalizable. What about n equals -1? That seems like a case where that satisfies Ka equals -1 times pi. That's perfectly good. Why would I throw away -1? Well, yes. I mean, so in this case, you're right. What was our definition of K? My K definitely cannot be negative. I mean, that wasn't even what I was thinking. What I was thinking is, look, if you plug in a negative K value for a negative n, the form of the function is exactly the same up to a constant as the one for the positive n. So it doesn't really give you a new solution there. But I like what Jake is saying too, that look, this thing can't be negative, right? A square root is never negative, right? Things underneath are perfectly real and positive. So numerator is positive, denominator is positive. K can't be negative, but yeah, we can't have K equals 0 either. All right, so that tells me the allowed values of K. We weren't really interested so much in the allowed values of K as we are in the allowed values of energy. So the definition of K was shorthand for root 2 me over h bar. So that's got to be equal to n pi over a. And that gives us the allowed values of energy for different n's. These, remember, this is all for the case just L equals 0. We haven't done the other L cases. And amazingly, it gives the same energies as the infinite square well in one dimension. There's nothing profound going on there. We won't find those same energies when L is not equal to 0. But in this case, when L equals 0, you get the exact same collection of energies and allowed n values, okay? Oh, worksheet number 2. What's worksheet number 2? Oh, well, we normalized YLM. Here, let's normalize. I didn't really quite spell out the whole problem here, so it should say in problem 2, normalize R of R for the L equals 0 case for the infinite spherical well potential. Right? I mean, I have to tell you what potential we're talking about, but this is the context of the infinite spherical well potential. Remember, if we normalize YLM, the spherical harmonics, and we normalize R of R, then the entire wave function will be normalized. So in other words, we're trying to find that A that's up there in the upper right-hand corner for Rn of R. That's right. If you're using capital R and you're going to normalize that, then we need the piece of the spherical volume element, spherical coordinate volume element that goes with the R integral. So I need an extra factor of R squared next to the capital R squared. Okay, so what I need to do is integrate from r equals 0 to infinity, r of r squared. So I've got this function squared down here, times the r part of the spherical volume element. So I need to put it next to an r squared dr, which is kind of nice that cancellation takes place. And oh, and I'm sorry, I shouldn't be integrating from r equals 0 to infinity, but rather just from 0 to a. After a, my function is 0 out there, right? So, this is a little bit wrong here, right? I should say it's this or 0. It's this for r less than a, and it's this for r greater than or equal to a. That would be my full wave function, right? So I should be integrating the square of that from 0 to infinity, but the a to infinity part just gives 0. Okay. And well, let's see, that's a squared times the integral from 0 to a of sine squared k x dx, which is an integral we've done before. I mean, you could do it using elementary calculus kinds of techniques. But remember, when we're doing this, after those r's disappear, and you imagine just changing the variable r to x, integral of sine squared kx dx. That's like normalizing our 1D infinite square well kinds of solutions, right? So the a that's needed is still root 2a because we're doing the same integral here, right? So this is equal to, by the same reasoning before, as a over 2 times a squared. And we're going to demand that it equal 1. There ought to be a symbol for demanding that something is equal to 1. Like maybe we could put a little exclamation mark over it. Like I demand that that's, because otherwise it's sort of confusing. Like where did the 1 come from? I'm demanding that it equals 1, and therefore a is equal to root 2 over a. You can think back to your elementary calculus techniques for that. All right. So therefore, the normalized function looks like this. That's for Rn corresponding to L equals 0. Now, when we have L not equal to 0, we're going to get different radial solutions. Then maybe it's worth reminding ourselves what we're talking about, right? We've got a spherical region, and we're finding solutions in here. Let me try to draw it 3-dimensionally. So there's my spherical region. Here's the origin. If we, take n equals 1, that's going to be the lowest energy case, right? We found out that this function goes to a perfectly finite value as r goes to 0. So if I try to plot this as a function of r, right? Here's 0 as a function of r. And here's r equals a. It's like it goes to a perfectly finite value, and it's got to go down to 0 and then be 0 forevermore. And it can do it like that. We've got a sine of kr over r. So the amplitude of sine of kr would keep getting smaller as time goes on. It would sort of flatten out as time goes on. So either I've got to put the first 0 there, or I can find the second place where it crosses the axis and smoosh that in there, right? That means it's going to oscillate more quickly, just like our 1D infinite well does. I think I have this illustrated actually in the slides here. So let's go back here. Okay, so if we normalize each one of those, then the whole thing's going to be normalized. And that's the solution. So here's our completely normalized function, which is a product of we have a 1 over root 2 over a. That's the normalization we just found right here, plus a 1 over root 4 pi that we needed out in front. And so combining those constants together times the r dependence, and we found out when L equals 0 and M equals 0, which is required when n, well, we're taking L equals 0, and remember that m has to be in the range from minus L to L. So if L is 0, m can only be 0 too. So we've just found out that the normalized version of this wave function looks like this. Not only just as a function of r, but this is a function of theta and phi too. And there aren't any thetas and phis there. So that means it's constant as a function of theta and phi. You tell me the r, it has that same value for all phis and for all thetas everywhere at that same radial position. But as I move to different radial positions, it changes its value in such a way that it's going to, we've cooked it up so that it goes to 0 at r equals a and meets that boundary condition. Okay, so this again is picture of the L equals 0 cases, what this function looks like for different n's. Increasing n is going up here. So here's n equals 1. That's a smaller wave number, k. The function starts out at a perfectly finite value and goes to 0 at its first 0. For n equals 2, it goes down and its second 0 is placed at r equals a. For n equals 3, the third 0 is placed at r equals a, and so on. So it's doing the same kind of thing we saw before, where each time you get one more wiggle as you go up in n values. Okay, and if you actually scale it so that you line these up with the energies, we find out the energy spacing is getting bigger because of that n squared. As n gets bigger, the energy spacing gets bigger. So this is the kind of thing that Griffiths might have drawn, but I didn't see this picture in the book, so I found someone who had drawn it on the web and stole it from there. Okay, so that's just the L equals 0 cases. As a function of r, theta, and phi, this is what it looks like as a function of r, and it's constant as a function of theta and phi. So at any r, it's the same over that whole spherical shell at that r. Now, okay, now that we've done the L equals 0 case, the arbitrary solution is less familiar. We're not going to be able to just solve the differential equation. You have to do a series solution. Okay, so if you write down this differential equation, nothing comes to mind. There's no elementary function solutions that solve this for u of r. But you can do a series solution, and then you can make up names for the resulting functions for which you have the infinite series. And here they are. They have the symbols JL, which is a function of KR. That JL is called the spherical Bessel function of order L. And NL is called the Neumann function of order L. And Griffiths, I don't know how much he shows this, but at least he mentions that the Neumann function is not clear at all from here, but you have to look at the series solutions and intuit that the Neumann functions actually go to infinity as r goes to 0. Okay, and therefore, when I divide by r to get the r solutions from this part of it would be discontinuous, and therefore we're going to take that b constant to be 0. In other words, we're looking for continuous solutions. Psi has to be continuous, and so for r to be continuous, we have to throw away this because n behaves badly. J, the spherical Bessel function, doesn't behave badly at r equals 0. When you divide by r, notice there were r's out in front here. There's an r there. Looks like a subscript there, but it's not a subscript. That's multiplication of b by r. And so when we divide by r, those r's just go away. We're left with just the spherical Bessel functions. Here's the picture from Griffiths. L equals 0 is the ones we already found, right? So L equals 0 is exactly a sine function as a function of r, but then it's also divided by r, so the amplitude's getting smaller and smaller, right? And remember, it has that special property that as r goes to 0, he doesn't show the top of it, but it actually rounds out to a constant value up there. So it goes to the top of a hill as you go to 0. That's from the sine of x over x goes to 1 kind of stuff from L'Hopital. For L equals 1, that's shown with the dashed curve there. It actually goes to 0 as r goes to 0. And for L equals 2, not only does it go to 0, but its first derivative goes to 0. And for L equals 3, its second derivative goes to 0 at the origin. So it goes to 0 faster and faster as you go up in L, okay? But they all sort of generically oscillate up and down and their amplitude gets smaller, the same way the L equals 0 case happened, okay? So we found the solutions. They have this name, spherical Bessel functions of order L. And now we have to require that this function is continuous at r equals a. So when I plug in a, I better get 0. The function better go to 0. And therefore, the question is, well, what does Ka have to be? Well, unfortunately, unlike for the L equals 0 case, where these zeros are all evenly spaced, right? There's equal spacing between adjacent zeros, and that makes everything nice. For L equals 1, 2, and 3, and so on, the spacing is not uniform anymore. So Griffiths defines this particular symbol, which makes things look really confusing. Ka has to equal beta L NL, where beta NL is just a symbol meaning the nth zero of JL of X, or JL of R, if you like. So what that means is we're looking, you know, J, the smallest value of N is going to be 1. So in this case, the first 0 is wherever that location is on the x-axis. So for example, here's the L equals 1 curve shown as a dashed curve there. This x value, where it first crosses the x-axis after x equals 0, right? As a function of kr, right? This, before we put the a in there, this was a function of kr. So x is equal to kr here. When this first crosses the x-axis, that's what we would call beta 1, 1. That x value where it crosses the axis, right? Because I'm looking at L equals 1, and we found the first 0 after r equals 0. So we just found beta 1, 1. That's where that green arrow is pointing to on the x-axis. There's beta 2, 1, the second 0 of the J1 function as a function of kr, and so on. There's beta 3, 1. So, you know, that's somewhat confusing, but there's just a name given to those. Why give a name to it? Well, because then I can actually write down sort of a formula for E as a function of N and L, right? Now it doesn't just depend on N, but like it did for the L equals 0 case, but in general, it depends on L. And so it depends on those beta NLs, right? We just use Ka equals beta ML and substitute it into our energy relationship between energy and K to get the allowed energies. So here's all the allowed energies for all L's, assuming you understand what that symbol means. And here is the, you know, you got to find a normalization constant for these. That's sort of a pain, but to get the, you know, this function is 0 when r is bigger than a, and when r is less than a, well, it depends on L. We have some function for the r part that involves the JL. And then we have our usual spherical harmonics because it's a product solution. And we've got to choose this constant for each n and L so that it integrates to 1 when you integrate from r equals 0 to a, phi equals 0 to 2 pi, theta equals 0 to pi. Okay. A question, I better stop and pause. Questions? I was thinking, you know, maybe we should do another MATLAB project where we actually show as a function inside this sphere, maybe for a certain cross section through it, what the probability density is for certain low values of N, L, and M, right? And so you get an idea of what the shape of these wave functions look like for the infinite spherical well as a function of r, theta, and phi inside the sphere. The only thing is I've got to think about exactly what's a good way to display that. And of course, I have to do it myself to my own satisfaction to make sure it's doable in an easy way. But we'll see how time looks if we have time to spend a day in the lab one day and try to do it together.
It could probably work.
I think it would work. I think it's just so easy to look at this thing that I boxed here and just say, blah. Like, what I have zero intuition for that. And so part of it is, these functions are defined in MATLAB, or at least something not the spherical Bessel functions, but the Bessel functions are defined. Spherical Bessel functions are just almost the same thing. You can get them out of the Bessel functions. And so, the spherical harmonics are perfectly simple formulas. The Legendre functions are in MATLAB too. So all this stuff, the pieces are there. And just to get some intuition, oh yeah, we're talking about, different definite energy states. Speaking of energy, notice that the formula for energy depends on N and L, but it doesn't depend on M. Well, that sounds a little bit funny because I do have an M in there. And I realized when I was preparing for class that unfortunately, the same thing's happening in Griffith's book. There's two different M's, right? One is M for the E to the I M phi, and then there's an M for the mass of the particle. This M, of course, because it's like a P squared over 2M, this is the mass of the particle right here. But we're also talking about those integer M values, which can go between minus L and L in integer steps upward. And, Griffiths doesn't even seem to mention it anywhere. And I mean, there shouldn't be any confusion if you're really following along, but, it might be worth changing this one to a capital M just so you don't get confused here for the mass of the particle that we're talking about. And when we go to the hydrogen atom, that particle will be the electron mass. We're going to assume the proton really is so heavy it doesn't move, it stays fixed at the origin. The electron's doing all the moving, and so the potential it feels is a function of potential energy stored between the electron and the proton is a function of that radial distance between the two. Yes. I mean, later on, again, that's a good notation to use. Griffiths doesn't use that notation in this part of the book, or at least that's what I thought I looked up before class. You can correct me if you read it differently. But I think by the end of this chapter, when we're talking about angular momentum, we actually do talk about M sub L. And that's only because we're going to have two M's there. We're going to have M corresponding to orbital angular momentum, and then another M corresponding to spin angular momentum. So we really need an M sub L and an M sub S, but it would be a good idea to just start with the M sub L right here. Why not? When I write my own book, that's what I'll do. Okay, so the point was, this energy doesn't depend on that integer M. And so there's some degeneracy. There's lots of different states, all with the same energy. That means we have energy degeneracy. Okay, so for each L, there are 2L plus 1 different states of definite energy that have the same energy. And Griffiths makes the comment that you'll find out even for different potentials, the energy can never depend on that integer M, since in these three differential equations, here's the R equation. Come on, there we go. Here's the R, theta, and phi equation. Notice that M appears in the theta and phi equation, but E doesn't. The only place E appears is in the R equation. And though an M appears, that's the mass of the particle right there, the integer M doesn't appear here. And so E can never depend on M when we separate variables in this way. Of course, that's under the assumption that the V is just a function of R. Things wouldn't have separated out in the same way if V were legitimately a function of R, theta, and phi. Okay, you're supposed to read about the hydrogen atom for tomorrow. I put that up on the website yesterday. And we're going to start out again just by saying, I know the potential energy stored between 2 point charges. Here they're going to be the proton, which we're going to imagine is fixed at the origin, and the electron, which is some distance r away from the origin. And here's the potential energy function. And so if both of them have, charge Q equals E for the proton and minus E for the electron. And so we're going to use this for our potential energy function. And the goal is, I'm not going to start it now, but we got to solve this radial equation, right? We're done with theta and phi. We just plug those spherical harmonics in there for any problem where V just depends on R. Then we're done with that. All we have to, the only thing that's left to be done is to solve the radial equation, but it looks pretty hellacious. So we'll have to follow along with Griffiths. There are series solutions. There are lots of advanced series solutions that probably you didn't do in differential equation, where if you just try to get a straightforward series, the recursion relation for the coefficients is a nightmare. And so what you do is factor out some very definite styles of functions and then get a series solution for the remaining part of the function. And then you can get a simple enough series solutions that you can make some sense of it. So we'll do that starting next time.